So, welcome to this lecture. We will today continue from where we had stopped the last time, where we had formulated generative modeling, rather sampling from the perspective of divergence minimization, right, and said that you start basically the problem is that of sampling from an unknown distribution, and what we have are some samples or data points that are given from that are sampled from that distribution, and we have n of them IID sampled. Now, the idea was to start from an arbitrary distribution such as Gaussian and transform it into the distribution of interest, which is the distribution that we are trying to sample from via neural networks, which are function approximators. The idea is to adjust the parameters of that parametric function, which is the neural network, such that some divergence metric between the true distribution and the distribution that is imposed by the model is minimized. So, that is what we had seen the last time, and I had also talked about divergence metrics, right, which is a broad family of divergence metric called the F-divergences. Choose a convex function, you get a divergence metric with a particular property, right, and use that and solve an optimization problem over the parameters of the function that is transforming an arbitrary random variable to distribution of interest, and we are done. The questions that we have to answer were, when we do not know the underlying distribution, how do we estimate the divergence metric, and therefore how do we solve that optimization problem that we are trying to solve. So, that is the, and what choice of divergence metrics that we would do is the questions, are the questions that we stopped the last class with. We will take up some of those questions in this class and see how to proceed from there. Just a quick recap, we had what is called as data. Data are n samples that are drawn IID from the distribution that we are trying to estimate, and these, without the loss of generality, you assume that these come from the d-dimensional Euclidean space RD, right. That is what I represent with script X going forward. Now, the goal is to sample from the underlying distribution, okay, and the idea is to start from an arbitrary distribution and have a parametric function which is often a neural network, right. And by the way, when I write neural networks using these trapezoid, they are shaped in accordance with the dimensions of the random variables that goes as input and output. You know, for instance, in this particular case, typically the dimensionality of the input random variable is less than that of the dimensionality of the data that we are trying to sample or estimate. That is why you have this sort of a trapezoid where you have smaller length here and larger length here. You start with some dimension that is less than that of the ambient dimensions, and then have a neural network that is a parametric function, and define a divergence metric and solve this optimization problem to get the parameters of the neural network. That is the story. Now, as I said, the above setup becomes a sampler for Px, the underlying distribution, if the distribution that is being imposed by the model matches that with the underlying distribution. That is the goal. Now, the objective is to find an algorithm that would minimize the F divergence between Px and P theta without knowing both of the distributions, but having samples from both, right. So, what do we have? We are not totally blind, we do have samples from the underlying distributions Px and P theta. Do we have samples from Px? Yes, that is our data. Do we have samples from P theta? Yes, that is what the output of this neural network is. And one important thing to be noted throughout this course is that most of the cases, the samplers that we design are, or rather the neural networks that we construct are samplers themselves. There are exceptions, for instance, the diffusion models where the underlying neural network that we construct is not a sampler, it is an estimator for something else or some other parameter, but for most of the algorithm that we see, neural networks themselves are samplers in the sense that the output of the neural network is the sample that we are actually seeking, right. So, x cap, which is the sample from P theta, we have it because that is the output of our neural network. We have samples from Px, that is our data. So, we have both of them with us. Now, the question is, given that we have samples from both the distribution of interest, we have to estimate the underlying divergence metric, okay, that we are trying to optimize, and find an algorithm to solve this optimization problem that we have. So, that is the goal. So, just mention this, right. Samples from Px are actually the data set, whatever we have in the data set. Samples from P theta are outputs of g theta of z. So, note that it is a function of the input arbitrary random variable, and g theta is the parametric function that we are trying to optimize for different z, right. So, you sample a z, see the so called randomness, whatever it means, is actually coming from z. Neural network is deterministic. So which means that given a fixed input, neural network always gives you a fixed output. There is no randomness in neural network, right. So different samples of p theta are obtained from sampling from Z first, and then you pass it through the deterministic function called neural network. Now I am assuming that we know how to sample from normal distribution here, right. Do we? We actually do, because there are pseudo random number generators and which samples from uniform distributions, and we know how to convert samples of uniform distribution to samples of Gaussian distribution through those Euler transformations, right. There are deterministic fixed transformations that would convert a uniform random variable into a Gaussian random variable. I mean, whatever the rand n function that you use in all of these packages, right, that is what we are doing here, okay. And I keep joking, right, the funniest thing in world, or the funniest irony in the entire world is that we have a deterministic algorithm to sample from random variables or random distribution, right, pseudo random number generators. They are deterministic algorithms, but somehow magically we get random samples from random distributions there, okay. So assuming that we have samples from Gaussian distribution, every time we pass it through g theta, what we get are samples from p theta of x, okay, and we have both the samples of px and p theta, and we need to find the distributions now, okay. Now here is a recurrent theme that comes up in the course multiple times, and this is a key idea, okay, in most of the generative models that people have constructed. Now what do we need are estimates of divergence metric or some functions, okay. Now all these divergence metrics, as I defined in the previous class, involves integrals, okay, of some functions with respect to the density function here, right. Do you remember that the definition of F-divergence, right. So involved an integral that is computed over, or rather which is a product of a function of something times the density function, okay. Now we know that when we have a function, when we have an integral that involves that involves a function times a density function, we can express them as expectations. That is the definition of expectations. Now the moment we express something as an expectation, we can invoke all the statistical techniques that we have which approximate expectations using sample estimates. See, one idea is that of the law of large numbers, right. So which says that asymptotically, if you have enough number of samples, then sample mean approaches to true expectation. That is what we need, as long as these samples are being sampled from the underlying distribution with respect to which we are computing the expectation, right. So now the whole idea, I mean, we will see this theme recurring in almost all the algorithms in this course, where we want to estimate divergence metrics, and these divergence matrices are some form of expectation, write them as some form of expectation with respect to the distribution that we are interested in, px and p theta. The moment you can write them as expectations, right, you can invoke the statistical law of large numbers to estimate them, approximate them using sample averages. So that is what we have, that is it. Now while doing it, we will incur a lot of loss, in the sense that these estimates are statistical estimates, and the moment you talk of sample based estimates, you have the goodness associated with it. Your algorithm is as good as the estimate that you have for these expectations, that is it at the end of the day. Now for some of the divergence matrices, you will not even have an exact estimate for the expectations, so we will compute bounds on them. The moment you cannot estimate something, what is the next best thing that you would do? Try to found a bound on it and try to estimate the bound on it, that is all we will do. For some of the algorithms, we get exact estimates for them, and we can represent these divergence matrices exactly using expectations, in which case we can invoke law of large numbers directly. In some other cases, we cannot directly estimate the divergence or directly represent the divergence matrices using expectations. Therefore, we come up with some kinds of bounds on these divergence matrices, and then estimate those bounds in terms of expectations, and then invoke law of large numbers. That is the whole story. The rest is all algebra. What we will do is in this entire course, I summarize that in 3 sentences. Okay, so there is a divergence metric, and we want to estimate that using samples. We do not know how to compute integrals. Represent those integrals using expectations. The moment you do that, we know how to approximate expectations using sample averages using law of large numbers. That is all. Okay, we will see how to do it for a several class of divergence metrics now. That is what we are going to do now. Okay, any questions so far? Okay. So now I already explained this. The key idea is that integrals involving density functions can be approximated using samples drawn from the distribution, right. Here is the example. Suppose we want to compute the following integral of some function h of x with respect to some density function p of, I mean times some density function with respect to the underlying random variable x, where h of x is a function of the random variable and p of x is the density function. Okay. Now what do we have? We have samples drawn from p of x, which are x1 through xn, which are id px. Now we know that the integral itself is an expectation of h of x with respect to px. So here is a small homework. I mean, you know this already, but just for the sake of completeness I am saying, see this, when you write expectation of x, okay, what is it given by? X times px, isn't it? Now if we want expectation of a function h of x, this should have been h of x times the density function corresponding to h of x, because h of x is a composite function on random variable, it has its own distribution, right. Still we write the expectation of h of x also as an integral h of x px x, not the distribution of h of x. Do you know why? To take this as a homework and prove it, what you have to prove is that the expectation of h of x, okay, is equal to the integral h of x px dx. Note that h of x has a different distribution than px because it is a function of x. So this is called the law of the unconscious statistician, Lotus. Prove this, okay, it is a small nice result. I mean I am sure you would have done it in your probability theory course. If just for as a refresher, do this once, okay. So this integral that we are interested in is now an expectation of h of x with respect to px. It is with respect to px. I mean this makes a world of difference. Why? Because if it were with respect to the distribution of h of x, then we would need the samples from that distribution to for the law of large numbers to go through. Now since it is still with respect to the distribution of px, as long as we have samples from px, which is our data, we are done, okay. Now we will invoke law of large numbers that would say that if you take these, which is sample averages, for people who have not studied probability and statistics, this thing and this thing are the same. But for a statistician these things are very different. So this is an estimate of the expectation and they can behave very differently compared to what this expectation is. So law of large numbers tells you that if you take this quantity which is called the sample average, okay, this approaches the true expectation asymptotically. See now you know why data is the new oil. So now you know why companies like Nvidia make a lot of money, is because see these techniques historically speaking existed for almost centuries. People knew all this from the time of Gauss and Eulers and so on. But what did not exist was that we had no way to make this n go to infinity, right. We had 5 samples, 10 samples, 100 samples. Even a decade back when I was a student sitting at the other end of this table, a large data set would be something that has 10,000 samples. Now I would not give a 10,000 sample data set even as an assignment to you people now, right. So what has changed is this approximation, this asymptoticity that is needed for invoking law of large numbers is becoming a reality today, because the number of data points that we have today which on which these models are trained are of order of multiple trillions. Okay. So that's how this expectation, whatever expectation that we are approximating using sample averages, makes sense today. Okay. Anyway, the point is now we bypass the problem of computing an expectation using sample averages. So now we don't need the underlying distribution at all, because this quantity, which is the sample average, only asks us to know what the samples are from the distribution without knowing the distribution at all. So that's the idea. Is that okay? Now the idea is if the F divergence can be expressed in terms of expectations of functions with respect to px and b theta, then one can compute and optimize them, that is all. Finally we want to compute that F divergence. Once we compute it, we know how to optimize any function with respect to a neural network using gradient based algorithms. That is what we will do. Are we good? Okay. So this is the general philosophy. Now we will actually go to the details and look at the algebra. Any questions on this general philosophy of how things happen? Shall we move on? No questions, the state of no questions can only happen in two situations, right, where 100% comprehension or 0% comprehension, because anything in between will actually invoke questions. See, that reminds me of yeah, I'll good that somebody has a questions. So that reminds me of this nice anecdote one of my friends who has a PhD keeps telling me. So employability and the education should be expressed in the polar coordinates. Okay, he says this is how you write it. Now theta equal to 0 is no education, you are not employable. Theta equal to 2 pi is a PhD. Feel the rest, right? You end up at the exact same point. Yeah, so I'm not discouraging anybody from doing a PhD here. Of course, I just on a lighter note. Yes, you had a question. Good question. The question is, how do we ensure that the samples that we have are IID? Because we are making this very, this law of large numbers is only valid as long as data is IID. Now, if the data is non-IID, what would we do? Okay, two ways communities tackle this question. Okay, one way to tackle this is that, we know for a fact that if you build an algorithm or a sampler for one particular type of distribution, the moment the distribution gets shifted, the algorithm breaks. So there is an entire community of researchers who are looking at dealing with non-IID data. Now, how do we deal? Including myself, even in our lab, we are asking this question on, suppose you distribution changes, especially in places like healthcare, where suppose you have built a generative model on one type of clinical modality, let's say X-ray or MRI something. You want to do the same thing on, let's say, histopathological images, it doesn't work. That is a known fact. So how do you deal with non-IID data? By construction, there are ways to do it. That is one way to tackle it. The other way to tackle that is that, suppose you model all data in the entire universe using a single distribution, then all data becomes IID. See, that's how some of these modern algorithms are doing. So why do you think these models have now multi-trillion parameters? Is because they are making an assumption that, see, if you look at the evolution of how these models evolved, right? Initially, they were text-based models. So even today, when you, even though the APIs that you look at seem like one model for everything, they are invoking different models for different modalities. So when you ask some of these models to generate images, they are invoking some other model. For speech, there is some other model getting invoked, and so on. So by and large, they are treating that let's say, as long as the modality is the same, text can be modeled as a single distribution, and IID assumption is made. And that is why, if you want to model a distribution that has super multimodality, then the number of samples that you need for this to happen will increase. And that's why data, these models are data hungry. Those are the very good question actually. Those are the two ways to handle the issue of non-IID, especially, right, when you have small samples and you are building these algorithms. This IID assumption becomes a very big bottleneck, and that's why you need to incorporate that fact into your models already. Yeah. Yeah, so the question is, what if my distribution is continuously evolving? Related to what he asked, but he said, okay, I have trained on something, and the inference time you have a different algorithm, but now you are saying it is continuously adapting. Now that is one puzzle that the researchers are trying to crack right now. This is called continual learning. That's what we do as human beings. So now how do we make sure that these models evolve over time as the distribution is changing is an open question. And there are again multiple ways to do it. People have tried different ways to do it, but continual learning is a problem that still exists today, and yeah, so one needs to tackle that. Okay, so however, for as long as this course is concerned, everything or most of the things that we see are with an assumption that the underlying data is IID. Okay, okay, so let's continue then. So now our immediate goal is to express the F divergence in terms of expectations over Px and P theta, right? Because that's what we know how to approximate using sample averages. Okay, good question. The question is, uh, why are we starting from z, which is I mean, why are we starting from the normal distribution as an input to this parametric function estimator? Why don't we start with some other data set and then transform it into some other data set? See, that we do, so okay, see that we can't do. Suppose you start with the samples of px itself, right? What do you transform it into? Right? We want to estimate the distribution entirely, so this parametric function has to sample from the distribution of interest. Now, if you start from the samples of px itself, what do you transform it into? You can actually start it from an arbitrary distribution. You can start from any distribution of interest. However, the usual practice is, if you want to sample from a marginal distribution, you start from Gaussian kind of distributions. If you want to sample from a conditional distribution, you should always sample from the distribution of the conditioned random variable, right? See, if you look at ChatGPT kind of things that you do, there is an input that it takes. So that input, actually these ChatGPT and all these things that you see are samplers from the conditional distributions. We will get to that. As I said, right now we are assuming that we are sampling from the marginals, P of x. Now, when we see some of the algorithms, I'll tell you how to tweak these to start sampling from the conditionals. When you start sampling from conditionals, you should obviously not start from normal distribution, samples of normal distribution. You need to start from the samples of the conditioned random variable. That is what we do. In fact, that is our input prompt. Whatever you give as input prompt are actually samples from the random variable y, and we are sampling from the conditional there. That is why, when people say prompt engineering, all they are trying to do is, how do you effectively sample from the conditioned random variable so that the sampling from condition distribution becomes meaningful, is the question that they are asking. You can actually formulate that entire prompt engineering as a distribution estimation problem. We will look at that later. See, after all, mathematics is converting common sense into formality, so that what common sense cannot capture can be captured. So, it is formalization of common sense so that the gaps in the common sense are filled. That is why I mean, I keep saying this, mathematics is no more than language. See, think about it. Let us say this is the general philosophy of science actually. So, let us say that you have built a generative model, you are sampling some samples from distribution. Now, I would ask you a question, how good these samples are? How do you answer this? Now, you can make some human beings look at that and ask them to rate between 0 and 10 or something, and then ascribe a number and so on, right? Even there you need some numerical value. The idea is, things that you cannot quantify cannot be debated on. So, I keep saying this, right? One should not have an opinion debate, because opinion cannot be debated on. So, if somebody comes and tells you that you are a bad person, you can't debate on that because it is an opinion. There is no algorithm to quantify the amount of badness, and there is no instrument to do that. I mean, had there been one, then we can debate on that, but the moment there is an opinion which is not quantified, there is absolutely no debate, it is an opinion. So, we need math, right? Because I say that there is an optimization, unless you put it into an algorithm and an equation, there is no way to understand what is happening. So, precision is what is needed, and math as a language gives you that precision. No other language in the world has that precision. That is why we need math. It's not, we are not at all force fitting this here, right? It's absolutely needed, okay. Anyway, so let us move on. So, now we have to express the F divergence in terms of expectations over PS and P theta, and that is what we would do. To do that, let us see what we need. Lot of times students ask me this question, how did these people who came up with this algorithm actually came up with this idea? There are lots of researchers here, you need to understand how would you approach a problem, right. So, look at the form of this integral. Now, if you want to write this as an expectation, Of course, we can write this as an expectation over p theta of this function which involves the ratio of the density functions. However, this we are begging the questions if we do that again. Why? Because we all our problem is that we do not know the density functions, and how do we get to estimate the ratios of it? Now, somehow we need to bring this ratio of the density functions outside of this f and get it outside somehow. You understand? Now, how do we do that is the question. The question is, we have a convex function f of some arguments, we need to take those arguments out of that convexity here. You get it? Can we do that is the question. And people who have studied convex optimization should know this idea of conjugacy or duality of convex functions. Now, every convex function has something called a dual conjugate or a conjugate associated with that. Now, what does that conjugate do? Conjugate basically would disentangle the argument of this function and the function itself. So, that is the idea. Okay. Now, let us define what the conjugate of a convex function is. So, if f of u is a convex function, and please note that this u is a dummy variable, okay, and by the way, the function that is coming in the definition of f divergence is a scalar valued function, right. It is from r plus to r, remember. So, that is why everything that we do are scalars right now. I mean, at least inside the f function of the f divergence are scalars, because the ratio of the density function is a positive real number, it is a scalar. Okay. Now, if f of u is a convex function, then there exists a conjugate function f star of t, again t is another dummy variable here, defined as follows. It is defined as the supremum of this particular thing ut minus f of u. The definition of the convex function is a pointwise definition here. I am hoping that all of you know what a pointwise definition is, right. So, we are defining it pointwise, which is the supremum of ut minus f of u, and the supremum is taken over the domain of f. I mean, I have written this as maximum because people do not understand what supremum is, but I am hoping that everybody in this class understand what supremum is, because the bound may not be achieved, and that is why it is defined as a supremum. Here we have f star of t as a pointwise definition, which is supremum of ut minus f of u, and the supremum is taken over domain of f, which is the starting function. So, what is the intuition behind it? Can somebody tell me what is it, what is happening here? So, if this is the convex function that we are looking at, no, f of u, right, and this is the domain, to define what f of t is, what are we doing? We are constructing a lot of lines here, right. All this ut minus f of u are different lines. Okay, let me write it here. Let us say this is u, this is f of u, and this is some arbitrary u, and this is f of u, and what we need is ut minus f of u. Okay. Now, what is this line? This line has f of u as the intercept, correct, and u as the slope, and t is something that we can vary. Okay. And by doing this we can construct multiple lines here. So, how do these lines look? We need f of u to be intercept for all these lines, right. This is one line and we have to change the slope of this, this is one other line, this is the other line, and so on, right. We can construct multiple lines like this, and the question that we are asking is, which is the line amongst all these lines that would have the maximum value of that t, that is the value of the conjugate at that point in t, that is it. Make sense? Okay. That is the definition of the conjugate function. This is a pointwise definition. We are constructing a lot of bounds, the linear bounds on the value of that function at that point, at a given point, and we are seeing which one has the highest value. Come again? No, at a particular t, this is what it is. Yes, t will be constant. This is what we are looking at. T will be the slope, u is what is going to vary. So, the question that we are asking is, we are fixing the intercept. Okay. What value of my slope gives you the maximum bound at that particular functional value is the question that we are asking. It is also called the Fenchel conjugate of a convex function. Okay. So, now we got this conjugate function. Now, the properties of the conjugate is, please take this as homework and prove all of this. Okay, the property of this conjugate is this: you can show that the conjugate is also convex. If you take a convex function, the conjugate of the convex function is also convex. The other thing is, if you take the conjugate of the conjugate, you get back the recover back the original function. The conjugate of the conjugate is the original function. That is the other property of it. So please show these two properties. Now, okay. Now, how do we use this? Remember our goal. Our goal was to represent the F-divergence in terms of expectations involving these things, right? Now, because the conjugate of the conjugate is the original function itself, the original function f function that we have now can be represented in terms of conjugate of its own conjugate, right? How do we define this? We define that as supremum of tu minus f star of t, where the supremum is taken over the domain of f star. Suppose a water bottle, right? A filled water bottle. Okay, so you got this definition. See, please note that this f and u are dummy variables, but I am fixing it. U represents the domain of the original function f, and t represents the domain of the conjugate, and therefore f of u now becomes, because the second property tells you that the conjugate of the conjugate gives back the original function, f of u can be represented as supremum over tu minus f star of t. See, writing the previous thing as ut and this tu only shows you that what is the domain that I am operating on, that is all. Is that all right? Okay. Now we will use this result in our F divergence. That is what we are going to do. Okay. Okay. So now F divergence is given as p theta of x times f of this ratio of densities. Now this ratio, this is what we write as f of u. Now u is the ratio of densities that we have, correct? Now replace f of u using its conjugate, which is supremum of tu minus f star of t over t. That is what f of u is. Now f of u here is f of the density, ratios of the densities, correct? Okay. Everyone with me so far? Now f of u, which was there in our F divergence, now will be represented as supremum of tu minus f star of t dx, where the supremum is over t, and now u is the ratios of the densities. Are you with me so far? Okay. I am just opening that up. So this is integral p theta of x supremum t times px divided by p theta of x minus f star of t dx. That is what we have, and this entire thing is what our sorry, this thing is u and this thing is f star of t by definition. Shall we continue? Okay. Okay. So now going from this step is from this step to this step is the crux of this entire algebra, and then the rest is very easy. Now, okay, let me explain that, and then I will go through the formalism here. See what is happening here. Now, what is our goal? Our goal is to represent this entire thing as expectations. If we have to do that, we will have to bring the supremum out of the integral. Okay. Now, if we have to bring the supremum out of integral, I mean, can we bring this supremum out of integral just like that? Why? What is the constraint? The supremum is over t, integral is with respect to x. Despite that, I mean, it looks like we can actually push the supremum out because it is with respect to t, but can we do that? Why? Come again? The supremum is pointwise defined, one, and exactly. So that is exactly what we would do, right? The idea is that the supremum is pointwise, okay, and what we have inside is a function of x. You cannot just bring this t outside and still make it pointwise, while the objective of the inner optimization problem with respect to t is a function of x. Okay, how do you solve this problem? To solve this problem, push this supremum out, and now that supremum will not be over t, but will be over a class of functions. And what are these functions? These functions are from x to domain of f star. What is domain of f star here? that is what I have been saying as T. So, the optimization which is the pointwise optimization over domain of T that we started with, when we push this outside of the integral, that becomes an optimization problem over functions instead of variables. And what are those functions? Those functions are functions from x to t, small t of course. So, can somebody tell me why is this the case? Why is this t got converted to a function on t? I mean, I have my explanation that I will give you in a while, but I would like to hear from you. So, what do you think is the reason this happened? Have you seen this before? So, has anybody taken an analysis course here? Real analysis, function analysis? Nobody? Okay, surprised. Okay, why would this become a function? You told me that it becomes a function, right? Do you know why? Why did you say that it becomes a function? Yeah, that's exactly the way I would understand that. See, what's happening is here as follows, right? See, there is an optimization problem over a t here. So now assume that you fix a particular x here. The moment you fix a particular x and solve this inner optimization problem, you would get some value for this function inside, and that is the value that goes inside the integral for every x. Now, when you push it outside, unless you preserve that particular value inside the optimization problem, the integral does not evaluate to whatever the previous integral was. Now, you need a function, okay, that this is space of functions containing solutions for the inner optimization problem. So, you are looking at those functions. See, this whatever is inside here, okay, whatever is inside here is a function of x, and for every x there is a solution that you get for the inner optimization problem. When you push it outside, the function or the t that you choose has to be in such a way that it preserves the solution for the inner optimization problem for every x that you choose. Actually, this is a standard trick in analysis, right? When you have a supremum involving a variable inside the integral with respect to another variable, when you push the supremum outside the integral, that optimization problem will now become a function with respect to a function which would map, okay, the variable of integration to the optimization variable that is inside the integral. Does not matter. I mean, I am assuming either. Come again? Agreed. That is why now this F divergence will become a bound, precisely for that reason. Since we are looking at supremum and not the maximum, and since t cannot attain, or rather the class of bag of t that you are looking at may not even contain a t that would achieve it at all the points, instead of having an equality we will have a bound here. That's my next argument. Yeah, it's a nice observation that you made. Okay, so the explanation is the inner optimization problems involves x, and the solution for it is actually dependent, which is a function of x, and that's why when you push it out it becomes an optimization over functions, okay, involving all functions that start from the domain of x, which is script x, and the range of that function is domain of f star, which is the optimization variable with respect to which we are solving the inner optimization problem. Okay. Now what happens? We bring it out. The moment we bring it out, the integral is as it is, and now as he rightly pointed out, since this script t, which is class of all functions, okay, that maps from x to domain of f star, may not have that one particular t that would give you the solution of this inner optimization for all x, which means that it is not attainable. We would have a bound here instead of the equality. The best case, it can achieve equality. I mean, it can, this t of x can be that function that would give you the solution for the inner optimization problem at all x. That is the best case. If it is not attained at all x, then you will have a bound on the integral that you are trying to estimate. Are we good so far? This is actually the most interesting stuff. The rest is actually algebra. We will quickly run through it. Any questions here? Yeah, so that is what I have written here. The space of functions t that we are optimizing over may not contain the optimal t star of x. Therefore, that it is not achievable, and that is which is the solution for the inner optimization problem, and that is why you get a bound instead of the exact equality. And this is again a standard trick. Whenever you have an integral and a supremum inside it, no, if you push it out, the integral now becomes a an inequality instead of the exact equality, because that the class of functions may not have that particular thing that is achievable. Okay, come again, because supremum, no, and we are looking at integrals. We are looking at integrals here, and all of these are positive real numbers, density functions, and we are looking at supremum. It can, whatever you have can only be greater than that. I mean, whatever you compute inside it can only be less than what you actually want to compute. Yeah. Okay. So now rest is quick algebra that we will quickly run through, and you expand this thing. Now p theta and p theta here gets cancelled inside the integral, and you have integral px tx dx. Okay. The next thing is integral p theta x f star of tx dx, and it was f star of t. Now it will become f star of tx dx, right? So which, and now we got what we wanted. Now this integral is an expectation, the second integral is an expectation. So integral p of x tx dx is expectation of tx with respect to px. Integral p theta of f star of t of x is expectation of f star of t of x with respect to p theta. Have you seen this equation before? This is the so called loss function of these generative models called generative adversarial networks. Okay. So, you know, people tell you all kinds of stories, right? There is a generator, there is some other discriminator, and these things are trying to compete with each other. There is a counter terrorist, all these kinds of things. I don't like that story. This is how you get this sort of, we still don't have adversaries, by the way, we will get to that. You know, we'll get into what is called as a saddle point optimization problem in a while. But yeah, so this is what it is. Finally, now what happened is that we constructed a bound on F divergence involving expectations of functions, and these expectations are over the distributions whose samples we have. That is all we wanted. Okay. Now we can approximate this expectation using the samples, and we can approximate the second expectation with using the samples. Now the question is, how do we get t of x and how do we get f star of t of x, which we will see in a while. And what is t of x? You know, t of x is all functions, okay, that map from x to domain of f star. How do we get an estimate for it is something that we will look at right now. How do we implement this is something that we will look at, but we got to the goal that we started from, which is express the F divergence in terms of expectations on px and p theta. But we had to pay a price. The price that we had to pay is we had to sacrifice equality for a bound. It's okay. I mean, that's whatever we have is what we have. Okay. Okay, we still have time. Any questions so far? Come again? Not necessarily. Depends on F. So we saw that the definition of F divergence depends on F. So you choose a convex function, right? That will define what f df is. So you choose an f function that will define what your f star is, and that defines what the domain of f star is. We will see different choices of f function that we would make will give rise to different f stars, and different f stars will give rise to different domains of f star. That is what is going to happen. T, which is again T is domain of f star always. Not anything, T is always domain of f star, no? I mean the symbol T was used for this domain of f star always. See, look at the convex conjugate, right? It is the supremum is over domain of f star always. The range space of this this function capital T of x is always domain of f star. F star of defined as? No, that is what I am saying. It depends on domain of f. T is defined over the supremum over U, which is on domain, which is domain of f. It is pointwise defined as a supremum over domain of U, and therefore it will have its own domain. And this T of x, the function, the range space of this function capital T of x is always domain of f star. This is very important because when we construct a particular type of generative model, we will have to be very careful about what function of t that we would choose, what f that we would choose, because we will have to construct our neural network in such a way that the final activation function respects this domain of f star. We will see that. Okay. Question? Yeah. Great question. The question is we are actually trying to minimize the f divergence. What we have constructed is a lower bound here, right? An upper bound is what is nice, because when we are solving a minimization problem, constructing an upper bound is not the greatest of the things that we would do. We want a lower bound on it, sorry, the other way around. We want an upper bound on it, we are constructing a lower bound here. I mean, what is this? Question is true, but this is all we can do. If you can come up with a nicer upper bound on this, you will have a nice algorithm, right? In fact, remember this, because when we go from this algorithm to, let us say, when these algorithms are notoriously hard to solve, we will see how why, and now we will the state of the art is, I mean, people still use this for different kinds of applications, I will talk about it, but most of the community has moved out of these kinds of algorithms, and now the state of the art are scale minimization, which is exact, which does not involve a lower bound here, because of one of the reasons is because of this, that while we are trying to minimize a divergence metric, constructing a lower bound on it and then minimizing it is not the greatest of the ideas, which is true. It is a nice observation that you made. Okay, shall we move on? Okay. Now this is called variational divergence minimization, by the way. These classes of algorithms are called variational divergence minimizations. Why variational? There is this entire field of mathematics called variational calculus, okay, which deals with this problem of how do you optimize with respect to functions. If you have an integral, right? See, I keep asking this question. One of my favorite use cases of variational calculus is, suppose you are given 2 points, okay. The question that I want to answer is, which is the curve that minimizes the distance between these 2 points? What is the answer? Huh? No, if you have 2 points in Euclidean space, let us say 2 dimensions or 1 dimension for instance, right, which is the curve that minimizes the distance between those 2 points? We all know this from class 5, right? Do you know that it's actually a problem in variational calculus? It's an optimization problem over function spaces, because the distance metric that we define, which is the Euclidean distance, is a function of that curve, which can be represented as a function. Now the optimization problem that we are solving is with respect to all possible functions that connect those 2 points, right? So the solution for that becomes a straight line, as we know of. You can actually show that it's a problem of variational calculus, where the optimization problem that we are solving is with respect to function spaces. The objective function is the distance metric between 2 points. So the question is, given that I want to connect these 2 points and there are infinite ways of connecting these 2 points, tell me that function which would minimize the distance between them, and it turns out to be a line. It is not obvious why, if you have 2 points, drawing a straight line between them should have the least distance. We take, see, this is what I am telling you. We take so many things for granted and we think that it's common sense. It's not common sense. See, do you know that 0 plus 1 being 1 is an axiom? Do you know the name of that axiom, by the way? Peano's axioms, right? We take it for granted. 0 plus 1 being equal to 1 is axiomatic. We build our entire mathematical premise using this, but now it's an axiom. Okay, so yeah, this reminds me of this thing, no, that Fermat's last theorem story that I keep narrating multiple times. Right, there is this mathematician by name Fermat. So he wrote a lot of mathematical proofs, etc., just like our Ramanujam, right? You know, where conjunctures after conjunctures without proof. Okay, just say that, okay, somebody came in my dream and wrote something like that, similar. You know, Fermat used to do that. Now there is this one theorem called Fermat's last theorem. This theorem is exceedingly simple. All it says is, x power n plus y power n equal to z power n, you can't find triplets x, y, z which are integers for n greater than 2. If n equal to 2, we can find those triplets, right? What are those called? They are Pythagorean triplets. So he said you cannot find any triplets for anything that is greater than 2. That's Fermat's last theorem. Seems exceedingly simple, but now somebody has to run through the entire space of integers, right, which cannot be exhausted to prove that. And the guy writes that I know what the proof of this theorem is, but the margin of this book is too small to write the proof, so I am skipping it. So he does this in I think 16th or 17th century, and people who came after him, all mathematicians, try to solve this, prove this Fermat's last theorem, failing. People like Euler tried, nobody succeeded in solving this, proving this. It was a British mathematician in I think 1990s, the 20-30 years before, solved it, got Fields Medal for it. And the funny thing is that he used mathematical tooling that were discovered after Fermat to prove Fermat's last theorem. Maybe there is a, see, the reason I remembered all that is something that seems exceedingly simple, right, is not simple, because it's very, we think common sense is very simple. It's not. I mean, formalizing common sense is all we have to do. And as I said, connecting, I mean, the shortest distant part between two lines, 2 points is a straight line, is not trivial. It's one of the first problems that we solve in variational calculus. Yeah. Why do we call this variational divergence minimization? Is because we are solving optimization problems over functions here. That's why it's called variational divergence minimization. But statisticians found a sort of a bypass for this problem, because they said, yeah, we have samples from it and we know how to represent integrals using sample averages, and we use that. So it's actually a bypass. If you ask mathematicians, this is not how they would solve variational problems. Actually, there are methods that would optimize over function spaces. But now the kind of function spaces that we are looking at, which are parametric neural networks with trillions of parameters, you can't analytically solve them. See, I keep joking about this. For all that optimization that we have learned over years, the one that has cracked intelligence is the first order gradient descent. So we study so many of them, right? I mean, second order methods and Hessian inversion, Newton methods, and so far, and all of them. But human intelligence and artificial intelligence is cracked using first order gradient descent, the naivest of all, which is what we use as backpropagation, and that is our workhorse even today. I mean, that's engineering versus mathematics for you, right? Anyway, so this is variational divergence minimization, or VDM in short, and we'll have to realize that variational divergence minimization. How do we realize that is the next question. Okay, so quickly we are given data and we have this setup here, and we constructed a lower bound on the F divergence as the supremum over expectation of this written as maximum. I mean, yeah, so it's actually supremum that what we have. Okay, so remember what our initial goal was. Our initial goal was to optimize the F divergence with respect to the parameters of this g theta function, isn't it? So optimization variable is theta. Now we wanted to minimize over theta df, and this df is we could not minimize that, and we constructed a lower bound on df. And now instead of minimizing df, we will now minimize the lower bound on df, right, which is see, note that from equality I changed it to an approximation here. Why? Because we are not minimizing the actual function, we are minimizing the lower bound on it. I mean, as he rightly mentioned, it's not the best of the things to do, but that's what we have. Now this is an approximation, and which is now equal to the lower bound itself involves an optimization over Tx, some other class of functions, right. So now the inner optimization is with respect to this class of functions t of x, the outer optimization is with respect to theta or g of theta, which is another class of functions. Now this will give us, okay, so now this will give us what is called as a min-max problem. So before that, what is done in practice is, see, we are engineers, so we have a function, we don't know what to do it, take a universal approximator and throw it to all kinds of function approximation problems that we would want to solve. And our holy function that we have, which we would always go to, is a neural network. Now you want to approximate, you want to represent t, throw a neural network to it. See, now you know where is this so called discriminator is coming from. It is an approximator for this T function. So we need two neural networks, one neural network which is a sampler, the other neural network which is an approximator of the optimization function with respect to which we are constructing, I mean we are the one that we are using to construct the lower bound on the divergence that we are optimizing. Okay. So now represent T using another neural network and call that T W of x, where W is the parameters of the neural network. Okay. Now if you do this, then our objective function that we would want to optimize will involve this min-max problem. We want to optimize the same objective function with respect to we want to maximize that with respect to W, which are the parameters of T function, and once we construct the lower bound, we want to minimize that lower bound with respect to theta, which is our sampler. That is it. Is that all right? This kind of optimization problems, right, which involves an objective function, and we want to maximize that same objective function with respect to one set of parameters of that function, and we want to minimize that same objective function with respect to other set of parameters of that function, are called saddle point optimization problems. See, in typical optimization paradigm, we want to avoid saddle points, but here is an optimization problem that deliberately seeks saddle point, and that is why training these are difficult. Okay, because we are explicitly seeking saddle points here. And please note that this entire function that we have inside this bracket, our objective function, is both a function of W and theta, right. That is what saddle point is all about, right. I mean, saddle point of a function in some parametric spaces, a point such that if you move around one particular variable, then the function increases. With respect to the other variable, the function decreases. That is what a saddle point is all about, right. So this entire thing is a function of theta and W, and we are seeking a point, okay, on that function space spanning theta and W, such that if you move around W, the function should decrease. If you move around theta, the function should increase. That is the saddle point optimization problem. Okay. Any questions so far? Yes, we will see that all the expectations are computed via samples, because that is all we have, no. Yeah, we do not have anything other than samples now. Okay. How much time do we have? 5 minutes. So maybe we will talk about the implementation of this, practical implementation of this in next class, because it's better done in one sitting. So what we will do next is that I will tell you how to implement this in practice, right, how these expectations will turn out, and what is the choice of f star that we would have to do, and how does the gradients flow here, and so on, so that we complete this variational divergence minimization as an optimizer. Okay. That is what we will do the next time, and that is all for today. When you come to the next class, please go through whatever we have done, so that when I say that we have a saddle point optimization problem that we are solving, you know what I am talking about. Okay. Okay, so also brush up your neural network training fundamentals, because the next class I will tell you that the gradient will flow from here, flow from there, and you do backprop here, you keep this constant, you keep this, you do not train this, etc. So brush up your neural network training foundations, right, backprop and what happens with all that. Okay. Okay, so that is it for today then. Thank you.